Lesson 14.1, Task 3. Graph geometric sequences. You can use the position numbers and terms of a sequence to graph the sequence by plotting the ordered pairs n and f of n. So that's like x and y. We use x and f of x. This time we're just using a different variable. So n and f of n is just the same thing as just your ordered pair like x and y. So the function is a discrete function. Remember, discrete means you do not connect the points. So its graph is made up of unconnected points. Graph the sequence f of 1 equals 2, f of n equals 4, times f of n minus 1 for all n between 2 and 5. All right, so it says you can use the recursive rule to make a table of values and then plot the points. So my n's, my first n was 2, and then you can find each one after that by multiplying by 4. So 2 times 4 is 8, 8 times 4 is 32, and so on. So this gives us our first 5 ordered pairs. All right, so to graph these, well, let's see what this says. To find the next term in the sequence, okay, you multiply the previous term by the common ratio. All right, so to get this term, I multiplied this one by 4, multiply this one by 4 to get this one, and so on, and that's what this is saying right here. To find the next term, you multiply the previous term by the common ratio. All right, so now that we have these 5 points, 1, 2, 2, 8, 3, 32, all the way up through 5 and 5, 12, you can see that they have graphed these points on this graph. So our n, or our x-axis, is 0 to 6, and they're labeling this n since they're using n in this example. And they're using 0 to 600 so that all the points are included. So it looks like they're going up by 100, so they've changed their scale to 100 on the f of n, or the y-axis. All right, remember it's discrete, so you graph the points, but you don't connect them. So if you look at this, this looks like an exponential growth function, and it would be an exponential growth function because you're multiplying the previous term by 4, and 4 is greater than 1. So it is going to look similar to the last lessons that we looked at. All right, so it says explain why the points on the graph are not connected. Each point represents the position in the sequence, and there are no values in between. All right, so this is basically saying, like, it's discrete. You're not gonna connect this because you're talking about the position in the sequence. So the first number, the second number, the third number, the fourth number, the fifth number. You're not going to talk about 1.3, like in between. You're not going to talk about that position. There's not going to be a position there. It's kind of like when you're talking about number of kids, and they say that the average couple has 2.3 number of kids. Well, you can't have 0.3 kids, so that's just a number. But like discretely, you could only have 1, 2, 3, 4, etc. number of kids. Well, this is talking about a position, like a number, and we're only talking about like our whole numbers here. So you're not going to have this graphed in between. It's just going to be those set of points. All right, that's all for task 3. If you have any questions, please let me know. Lesson 14.1, task 4. Graph geometric sequences. Part of a geometric sequence is shown on the graph. You can write a recursive rule for this sequence. All right, so now they're going to give us points, and they want us to write an equation. They're calling it a recursive rule, but really they're just wanting us to write an equation. So remember the equation that I told you to write down in the previous task? Now we're going to use that. All right, so it says complete the statements to explain how you can find f of 1 from the graph. Okay, so f of 1 is 1 and 160. So it says find the blank coordinate of the point that has a first coordinate of find the second position. So we're looking for the 160, right? Because we know that 1 goes with 160. So find the second coordinate of the point that has the first coordinate of 1. And in this case, f of 1 equals 160. All right, then find the common ratio. So you can find the common ratio. So you can look at the y value minus the y value, or in this case, f of n divided by f of n. So 80 over 160 is 0.5 or 1/2. 40 over 80 is a half. 20 over 40 is a half. 10 over 20 is a half. So if you look at those positions, you can see that each one of these equals 0.5 or 1/2. All right, so the recursive rule is f of 1 equals 160. That's your first term. And then 1/2 times the previous term. And we label that by f times n minus 1. N minus 1 just represents the previous term, okay, for all n greater than or equal to 2. So this would be your recursive rule. Not too difficult, just looking at the graph to find that. All right, so complete the statements to explain if it is possible for f of n to be a negative number. It is not possible for f of n to be a negative number because the common ratio of the first term are both positive numbers. You can see that 80 divided by 160 is positive. Obtained by repeated multiplication, all subsequent terms will be positive numbers. Getting tongue-tied here. All right, that's all for task 2. If you have any questions, please let me know. Lesson 14.1, Task 5. Apply geometric sequences. Micah read that a high school student was able to fold a long piece of tissue paper in half 12 times. Micah folds a piece of notebook paper in half as many times as possible. The table shows Micah's results where f of n equals the number of layers of paper after n folds. Graph Micah's results and write a recursive rule for the sequence. How many layers would there be after 12 folds? All right, so you can see the first time he folded it, then there's 2 layers. The second time he folded it, there would be 4 layers, and so on. So he folded it 6 times. After 6 times, there were 64 layers in his stack here. All right, so you can plot the points n and f of n. Again, remember that's just another way to write x and f of x, or x and y, to make a graph of this sequence. So n is in the x position, so it's always along the horizontal axis. So here's n. So we're going to graph 0 to 6, and that's just straight out of number of folds. Okay, and then f of n is my y-axis. It's going up the side, and the number of folds goes from 2 to 64. So that's why it goes from 0 to about 65 or 70 here, just so it includes all of those points. So these are graphed. These are the points. Your n and f of n is just like your x and y points graphed along here. And again, we do not connect these because this is discrete. These are just ordered pairs. All right, so it says complete the statements to explain why the sequence for the number of layers for the folded piece of notebook paper stops at n equals 6. All right, so the n coordinates in the ordered pair represent the number of, all right, so you can see the n coordinate represents the number of folds for a regular piece of notebook paper. The blank number of folds of a regular piece of notebook paper will be, so the maximum number of folds would be 6. This is fewer than the folds you can apply to a piece of tissue paper based on each paper's thickness. So you know notebook paper is going to be a little bit thicker than tissue paper. Tissue paper is pretty thin and would probably fold easier. Not sure if you could fold it 12 times, but you should be able to fold it more than 6. So that's why it says folding a piece of notebook paper would be folded fewer times than tissue paper. All right, the sequence is geometric because consecutive terms have a common ratio. So you can write a recursive rule for this sequence. So f of 1, so if you look back up here, your first term was 2. And then you can multiply by 2 to get to each term after that. So your rule would be your first term is 2, and then f of n equals 2 times the previous term for all n greater than or equal to 2. So it says, why is the common ratio 2? The ratio of each term divided by the preceding term equals 2. That's true. The piece of paper is folded 2 times what was folded more than 2 times. Each time you fold a piece of paper, the number of layers doubles. So that one is true, and this one is true. All right, it says you can find the number of layers after 12 folds. That's true. So all you had to do was take the previous term and multiply it by 2, and you can go all the way up to 12 folds. All right, so it says complete the statement to explain why you have to find 7, 8, 9, 10, and 11 before finding 12. Well, when you're doing recursive, you're always multiplying by the previous term, so you can't jump to the 12th term until you find the previous term. So 7 comes from 6, which we were given the first 6. So then we found 7, 8, 9, 10, 11, and 12 to finish that off. All right, so it says complete the statements to explain why you have to find 7, 8, 9, 10, 11, and 12. The sequence is defined by a recursive rule. To find any term, you need a common ratio and the preceding term. All right, so there would be 4,096 layers if the paper was folded 12 times. So again, I think that's impossible with notebook paper. I'm not sure that's possible with tissue paper, but feel free to try it out if you like. If you have any questions, please let me know.